Yeah, I'm very happy to be here. So I'm going to be talking about learning quantum states and Hamiltonians, or more broadly, the intersection between learning and quantum simulation. And I will mostly be writing on the board here. I'll try to make it as large as possible. I heard people sitting in the back sometimes had a hard time watching it. So if I start to write too small, feel free to just let me know. And also, if there's any question in the middle of the lecture, just raise your hand and ask. And also, some part of my lecture was designed to be more interactive. So I'll pose a few kind of questions to you guys, and hopefully you guys could think a bit about it, think what's the best way to answer these questions, and so that I could try to gauge how well the materials are. And so let's get started. So for some of you that haven't heard about this field before, this learning quantum states or learning and the intersection of quantum, let me just try to first start by introducing a very simple, or one of the most basic setting or problem that people study in this subfield of quantum information science. So in this subfield, we're usually interested in some unknown quantum state or unknown quantum dynamics or unknown quantum device. What do we mean by that? So in the simplest form, we consider that in the experimental lab or on an analog quantum simulator or on a digital quantum computer, we have generated some many-body quantum state. So rho here is the density matrix, is 2 to the n by 2 to the n matrix, quasi-semi-definite and has trace 1, that correspond to some n-qubit state that we have created in the lab. And here, this is us. We're sitting next to it as a scientist, trying to understand what's happening in the quantum device. So how can we think about this state rho? So one can think about this state rho as, for example, the output of some analog quantum simulation. We just try to write down some Hamiltonian, try to implement that Hamiltonian in the lab, try to evolve it and produce some output state. It could also be something more complicated. So for example, recently there have been a lot of development in Gibbs sampling that is try to utilize thermalization processes, try to mimic nature's thermalization process on quantum computer in order to prepare thermal state. So thermal state are essentially also known as Gibbs state. They're just at some finite temperature, at some temperature, there's going to be a density matrix associated to some Hamiltonian that we cared about, and that's called Gibbs sampling. So we can think of this rho as the output of these Gibbs sampler, that during the conference there's also going to be talks about this subject. And this doesn't necessarily have to be output of some quantum simulation. It could also be, say, the solution vector that was stored in the quantum state that was obtained from, say, linear system solver like HHL, etc. It could also be the solution vector for solving some partial differential equation. It could also be like a trial state, like a variational ansatz that was generated using a variational quantum circuit. Or it could just be the output of any quantum algorithm that we run on the quantum device. So sometimes the algorithm might be corrupted due to noise, and hence the output would be a density matrix. Or maybe we're using fault-tolerant quantum computer in the future, and then the output would be a pure state. But in general, it's always a rho that was written here. So that will be the main kind of target of interest. We're interested in understanding the state rho that was prepared in the lab. So the main question in this subfield that motivates, or kind of the motivating question of this subfield of this field is to understand how to efficiently extract information from this state rho, this n-qubit state. So note that in all of these settings, we're going to create the state rho if the algorithm is running successfully on the quantum device. But us as a classical being, we cannot really just see what's happening in the quantum state. Like we run some quantum simulation, try to prepare the ground state of some Hamiltonian. Say eventually the algorithm succeeds in creating such a state rho. We cannot just see it. It's just lying there inside the quantum system. And in order to get useful information out of the quantum simulation, we have to perform some kind of learning. We have to try to extract information say, getting observable values out of the state that we have obtained, etc. So the key question is basically this. We have created such a state role in the quantum device, and now we would like to be able to extract information from it. So that's this extraction of information, more broadly speaking, is called learning. So another way to phrase the question is how to efficiently learn the quantum state role. And that's going to be the main question that we try to address in these 2 lectures. So now let me begin by talking about what is the traditional approach that people take to answer this question. So the traditional approach is known as quantum state tomography. Traditional approach. Probably many of you have heard of this term before. So the idea of quantum state tomography is to really learn the entirety of this unknown state role. So we think of this role as a state that was in the quantum device, and now our goal is to really fully capture this entire exponentially large matrix. And since this matrix is exponentially large, all the resources scales exponentially in the system size. So state tomography, it's very well known that it would require 2 to the order n, actually 2 to the theta n number of, say, measurements, as well as computational time, just to process all the exponential number of measurement data, or memory, because even the representation is an exponentially large matrix, and etc. So other resources include like how many times we need to keep generating the state role in order to run state tomography. That's called sample complexity or copy complexity. But essentially, it's well known in the field that in doing state tomography, the scaling is exponential, because we're essentially trying to learn an exponentially large matrix. And hence, that's highly inefficient. So instead of highly efficient, especially now, like nowadays we have hundreds or even thousands of qubits, like in atomic systems, people were able to create devices, analog quantum simulator with hundreds and thousands of qubits. Then in that case, this state tomography approach for learning and extracting information from role would be highly inefficient, and hence one needs to try to find even more efficient or better way of doing it. And one of the new approach that have been coming up these days is known as shadow tomography. So just to poll around, like, how many people here have heard of shadow tomography? If you have, okay. A lot of people do know. That's very nice. So yeah, so shadow tomography, the idea is to be able to predict many properties directly. And the common setting is the following. So instead of trying to learn the entire state role, the goal is to just directly predict many properties. So one of the common setting is that we consider many observables, O1 through OM. Think of them as n-qubit observables. And the goal in shadow tomography is to do the minimal number of measurements, or use the minimal number of copies, in order to predict the expectation value of all of these observables up to an epsilon error for all I from 1 to n. So that's the main question. Another Yeah, another question for you guys. Do you know the kind of the inner working of shadow tomography, like the analysis and like the theorems and so on? Like if you do know, then could you raise your hand? Okay, so there's less. Yeah, I was slightly worried that you guys already know everything I'm going to talk about. So. Okay, then even though you've heard about shadow tomography, sounds like for many of you, it's still not entirely clear what is like what are some simple protocols for achieving this task efficiently, and some of the kind of the theorems and the properties that, like the analytical properties of it. So that's what I'm going to talk about next. So one of the, I hope it's okay to just erase this part. This part is pretty trivial. So one of the simplest algorithms for doing shadow tomography is called classical shadow. It's really a very simple algorithm that a lot of people have already been using it in their experimental platforms for learning about their quantum systems, etc., due to the simplicity of this method. And yeah, so it is one of the most simple protocol for solving this shadow tomography problem. That is, we wanted to learn a large number of observables using as efficient or using as few measurements as possible. So this protocol contains two main phases. One is the data collection phase, and then the second one is the kind of the data analysis, or one can say the prediction phase. So let me begin with the first part on data collection. So this classical shadow protocol, it's once you think of it as a framework, it's a formalism for learning about quantum system. It's not a single protocol, but a family of them that one can have. One have the freedom of choosing the inner working of it. But the general framework look like the following. So in the data collection phase, we will consider running the experimental procedure to prepare one sample of rho, of the state rho. And then the next part is the important. So at every round, we will sample a random unitary. So this is a random unitary that's being sampled. So one can think about it as this unitary is being applied onto rho to scramble the quantum information inside. And then after scrambling it, we will perform a measurement. So here, when I say measurement, I will always restrict myself to performing standard basis measurement, or z-basis measurement, or computational basis measurement. And we assume that that's the only measurement that we can do on a quantum device, which is pretty common for many systems. And yeah. And by performing a measurement on an unqubit state, it would generate a random bit string, BT. Think about it as it's just, it consists of n bits. And that's the measurement outcome when we perform it. So the reason I said this is a general framework is because there's a lot of freedom in choosing what the random unitary is. We can choose the random unitary to be the uniform distribution, or we can sample it according to the uniform distribution over all possible unitaries, or we can sample it from some subgroup of the unitary group, or we can sample it in some arbitrary way. So UT can just be, say, a Hamiltonian simulation. We just sample some random Hamiltonian that is possible by the device and by the platform, and then we just evolve it for a random time. That's also fine. So there's a lot of freedom in choosing that. But one of the key properties, or one of the key identity that we're going to use is the following. So the idea is this. If we now wanted to utilize the measurement data, like what we get out of here, as well as the knowledge of what we applied here to scramble the system in order to figure out rho, first intuitive guess would be just take the computational basis state that we obtained and now kind of inverse evolve it. So since we first apply ut to rho and then measure, and we get this result, intuitively it felt like in order to get some representation of this state rho, we should just take this bt and then go through the inverse to create this state. So sometimes this state could be quite complicated, but if we restrict ourselves to certain random unitary, like it's a Clifford circuit or it's some short time dynamics, then this state will have a very efficient classical representation that allows us to understand and manipulate it efficiently on classical computer. So most of the time one would restrict to that setting. So for example, if this is a 1D short time dynamics, then this would just be an MPS or MPO. If this is a Clifford circuit, then this would just be a stabilizer state, both of which can be analyzed efficiently. So a key identity that one gets, or one would utilize in this framework, is that if we take the expectation value over the bit string that we got out, as well as the expectation value over what random unitary that we're sampling from, then one can show that this object, so this is, of course, also an exponentially large matrix, but as we discussed, in many cases, this has efficient classical representation. If we now average over the randomness in B and U, then the resulting state, one can prove that, which I'll do so soon, that this would be equal to applying some quantum channel M to the unknown state rho. So note that rho is unknown to us. It's just something prepared in the lab. And now all we see is this guy. But now if we average over the randomness in the scrambling dynamics as well as the bit string, then one can show that, first, this is actually not equal to rho itself, but it's equal to a quantum channel applied onto rho. So is it clear to you that this is quantum channel applied onto rho? Like if it's clear, then raise your hand. Oh, okay. But just to make it even clearer, like why is this a quantum channel? We can write out the explicit form of it. So the explicit form looks like this. We're essentially averaging over U, and we consider all possible bit string B. And now with probability B, U, rho, U dagger, B, that's a real number, that's the probability that we get B, we will create U dagger B, B, U on the system. And hence, from this formula, one can essentially show that this is actually a CBT map. It's kind of like a measure and prepare channel. We first take rho, randomly rotate it, and then measure. Now we get the B, apply U dagger, and then prepare. So it's a measure and prepare channel, apply onto rho. So now from this relation, we can immediately, or we can just change the formula a little bit. Like we apply M inverse on both cases. Then now suddenly, we apply M inverse on both sides and use the linearity of the expectation value, and now we will get the following identity, which is if instead of just doing U dagger BBU, after that we apply it's still a linear map, an M inverse onto it, then the expectation value of this object, this exponentially large matrix, which can be represented efficiently classically in many situations, will now be equal to the unknown state rho. And hence, we can just utilize this object kind of as like a surrogate of our unknown quantum state rho. So that's the basic idea behind classical shadow. Maybe I'll keep this.
Dr. Huang, do you need to use the board below it? And you can slide it up.
Oh, okay. Maybe that's a good idea. Yeah. So now, basically for each of the measurement data, we can define sigma hat t to be equal to this object and inverse ut dagger bt ut. And that identity shown there essentially tells us that if we take the expectation value over sigma hat t, this will be equal to rho for all of the measurements, for each of the measurements that we consider. And here I'm going to assume that we perform capital N number of measurements, and hence t ranges from 1 to capital N. Now, there are two simple examples for understanding what the sigma hat t are. So the first example is when U is a random Clifford. In this case, the measurement channel has a very simple form. So how many of you know what the measurement channels for this case are? Yeah, it's depolarizing. Just to check check a bit on, if you know what it exactly look like, please raise your hand. Oh, okay. Then I'll go through it a little bit slower. But basically, in order to derive this measurement channel M, what we need to use is what people call a two design property of a random unitary or random Clifford circuit. So it's well known that the following holds. So let me just write down the identity. And so there are multiple ways to prove that the identity that I'm going to write down. But the most common way is to use representation theory to prove it. And it's a pretty standard representation theory, so I'm not going to talk about it. But a basic result from representation theory tells us that if we consider any state psi, and then we take like the dagger, and then we take two copy. So we take this tensor product with itself. And now suppose this U is sample from the uniform measure, also known as the Haar measure, like the uniform distribution over entirety of unitary group. Then this would be equal to 2 to the n plus 1 times 2 to the n. And then on top, I think it's identity plus swap. So here, identity meant, so note that there's two copy here. So there's n-qubit state tensor with another n-qubit state, the same state. And now the identity here just means it's an identity on two n-qubits. And the swap here means we're swapping the 2 set. And then there's a kind of a normalization factor that come out of it. So this is a basic fact. I'm not going to prove it. There are multiple proofs of this basic fact. So so now here's a simple exercise. So note that this identity holds for any psi. Now the question is, if I tell you this fact, this equality is true, then can you now explicitly evaluate what the measurement channel should be? So note that, first of all, here I said U is sample from Haar measure, but because of the fact that random Clifford circuit forms 2 design, and by forming 2 design means that when we have this moments of U, when it appears, U appear twice and U dagger appear twice, then the excitation value for U sample from Haar measure, it would be the same as when we have U sample from the Clifford group. So this is also true. And now, utilize this fact. It's a simple exercise, but try to derive what this measurement channel looks like. So probably wait for a minute or 2, and for someone that, if you figure it out, feel free to raise your hand and tell me what the measurement channel looks like. It shouldn't be too hard, but if you start to feel it's too hard, just let me know. Oh, you mean what does this mean, or? Oh, yeah. So this tensor is we first take this whole thing and then tensor. So it's on the whole state. Yes. If you figure it out, please raise your hand and tell me the formula. Did you figure it out?
Might be 1 over 2, 1 over the normalization factor times rho.
1 over what?
The normalization factor, that one.
This whole thing?
Yeah.
So you're suggesting that this is this times
Over rho times rho.
rho?
Plus another term that proportional to identity.
Some term proportional to identity?
Actually, I'm not sure about the factor, but yeah, just thinking about the identity as swap. And,
I see.
Yeah.
Yeah, that's very close. That's very close. Does someone want to correct it or?
Square root of the I plus 1 would be
You're thinking that there should be a square root?
of the quantity that you have below that.
You feel like there should be a square root of this object? Something like this?
Yeah, something like that.
That's closer. But still not exactly correct. But yeah, let me just share the answer just in case of time. It's very close. So first there's no alpha, it's just rho plus identity, I think. And it's almost like this. It's almost like the square root of this, but the actual answer is it's just 2 to the n plus 1. So let me give a quick proof of this. So we essentially just try to write down that term in a slightly different form. So we first pulled out the sum over b. Note that there's 2 to the n object that we are summing over. And then we use a kind of write it out in terms of like a partial trace. So think of it as there's two systems. There's system 1 and system 2, and we're just going to trace out the first system. And what are we going to do there? We write it in terms of this: rho, tensor, and identity. And then inside of it, we move the excitation value of u into here and write it in terms of like this. So this expression basically just means we consider two copies of u dagger BBU, one here and another sitting right next to it. And then we average over u. And now we multiply that with this subject. So the first row will be multiplied with one copy of it. And then the second identity would be multiplied with the second part of it, like the second copy of it. And now we trace out the first system, the system associated with rho. And by tracing that out, essentially it gives rise to this BU rho U dagger B. And then the second system would just be U dagger BBU coming from here. So I hope it's clear that this is equal to exactly the same equation that was shown above. I explicitly noted an n just to mean that this is over n qubit when we sample from the Clifford group over 2 to the n matrix. And now we just plug in. So for this part, we just plug in the identity that I talked about there. But note that now we pick psi to be the computational bit stream B. And that gives rise to identity tensor identity plus swap. And the whole thing would be over 2 to the n plus 1 times 2 to the n. So now I can try to evaluate the partial trace. And what one would immediately see is the following. So just going to write down the expression right next to here. It would be sum over b. There will be 2 to the n of them. That's important because that's going to cancel out the 2 to the n over there. And then when we consider multiplying I tensor I with this and then trace out the first part, it just gives a 1, or it gives an identity. And then on the other hand, if it's a swap, and then we trace out the first register, So there's a kind of pictorial way to think about it, because in a way, swap, one can think about it as, like in the quantum circuit, it's just swapping two registers. And now when we trace out the first copy, essentially have this tensor network representation. And essentially that leads to just a single row on one system. And then there will be 2 to the n plus 1 times 2 to the n coming there. But then, since this object has no b inside, so when we sum over 2 to the n of 2 to the n things, this sum disappeared and cancel with this. And hence, the answer just arises from there. So that's a That's a simple proof for the case when it's random Clifford circuit. The measurement channel, as some of you correctly pointed out, it's a depolarizing channel because it's just taking rho and then so note that depolarizing channel is like you take rho and then there's some probability and then yeah, another way. Okay, maybe that's to see that this is depolarizing channel. Note that this is the same as like we either put in. So with a very high probability, we're going to replace it by a maximum mixed state. So what's the probability? It's 2 to the n over 2 to the n plus 1. We're going to replace it by maximum mixed state. But then with 1 over 2 to the n plus 1, we're going to just keep the state rho. So that's why it's a complete depolarizing channel. Or it's a depolarizing channel, not completely. It's very close to a complete depolarizing channel. So that's a first example. And from there, there's a simple way to write down the shadow associated to it. So sometimes people call this sigma hat t to be the classical shadow or the shadow of the state rho. And given this identity that we have just derived, we can write down the shadow sigma hat t to be equal to, just take the inverse of it, just like moving it up and then minus identity. So it's just, here's the shadow that one gets from random Clifford circuit. So that's the first example. And hopefully the derivation is clear. I'll just erase it. So now for the second example. This one will be a bit faster. So we consider the random unitary U to not be just a random Clifford circuit, because a random Clifford circuit requires tons of entangling gates, like a bunch of CNOT gates inside. So sometimes for certain systems, it's not that ideal. The second example considers the case when there's no entangling gate. So U is just equal to the tensor product of single qubit Clifford gates. So think of it as when we are doing the protocol, the random unitary is just tensor product of single qubit random Clifford gate, and then we measure. So note that in this second example, it is exactly equivalent to, for each of the qubit, we just randomly measure in the Pauli basis. The reason is because if we apply an identity for a qubit, then we would just measure in the Z basis. But now if we apply something like a Hadamard, then we will be measuring in the X basis. And then Hadamard times phase gate, that will be like measuring in the, or phase gate times Hadamard, that will be measuring in the Y basis. And actually for any of the Clifford elements on a single qubit, it would just always map the Z basis measurement to one of Z, X, or Y. So sometimes people also call this situation a randomized Pauli measurement because we're just randomly measure every qubit in a Pauli basis. So by building on example 1, we can immediately write down what is the measurement channel associated to the second example. And the reason is because it's essentially just a tensor product of tons of n of this for n equal to 1. So the measurement channel is really just a tensor product of M1, where M1 corresponds to this measurement channel here, but with n equal to 1. So in that case, it's like 1/3 rho plus identity. And correspondingly, we can write down the classical shadow in this case. But here, I'm going to use the fact that in this situation, the unitary that we're applying also tensorizes. And we consider each qubit to be indexed by I. So I goes from 1 to little n. That's the index for each qubit. And the corresponding classical shadow in this case will look like this. So UTI corresponds to, for the teeth measurement on the ith qubit, what is the Clifford that we implemented? And then similarly, BTI corresponds to a single bit on the teeth measurement and the ith qubit. And yeah, so that's the formula for the second example. So feel free to write it down, and it shouldn't be too hard to derive both of them from example 1. So now after talking about the data collection and the construction of these shadows, so sometimes people call this the shadows. We would like to talk about how one can utilize these measurement outcome or these shadows to make prediction of the properties. So note that going back to our problem, the goal is to be able to predict these expectation value. Is there a question?
In these two examples, everything works out super nicely, but
Yeah.
in general, are you always guaranteed to find the closed form for the inverse map, for example?
Yeah, that's a great question. So in various cases, so these are one of the simplest cases, but in various cases, we can indeed find closed form for the measurement channel. But sometimes if the kind of the distribution for U that we're sampling from is too complicated or too specialized, like maybe it's just some strange chaotic Hamiltonian H, and we're just randomly evolving it under some random time. Then in that case, it's not so clear how one can write down a closed form expression for M. And in those cases, one have to resort to some numerical calculations to do so. So people have worked on various ways to address that issue. I think some of them focuses on short time Hamiltonian dynamics and consider M to be try to calculate M using tensor network methods and so on. So there are numerical ways to address them, But yeah, in general, and also approximate methods for addressing this question. But it's not always that there's such a nice closed form expression.
Yeah, what was here?
And what about the inverse, the M inverse? Is that always well defined? Maybe you said that I missed it.
So it depends on whether the channel M is invertible or not. Like sometimes the channel M might not be invertible. So here's a very simple example where that's the case. So if we actually, so here it's very general. So one could say, what if the random unitary I'm sampling from only contains one element, which is identity? I'm not going to do anything. I just measure it directly. Then in that case, one can still write down the associated M channel, but because the measurement is so limited, like the scrambling is so limited, in that case, this M channel would not be invertible because all that you're going to measure is like the diagonal part of your density matrix, and hence you're not going to see the off-diagonal part, and hence the M inverse would not be well defined in that case. But in those cases, one can still consider changing this to be like a pseudo-inverse. In that case, one can still go through the same formalism, but it's just that in those situations, there will be a notion of invisible space. So here, in both cases, the entirety of rho can be seen in the sense that if you do enough number of measurements, you will be able to learn everything about rho using this in these two examples. But now for certain distribution over U, that might not be the case. Like if it's just U equal to identity, always. Then in that case, all you can see, the visible space, is the diagonal part of rho, and then the off-diagonal part would all be invisible to you. But then one can still generalize the entire formalism to talk about how efficient one can learn the visible part, and of course the invisible part would just be unlearnable.
I see. Yeah. And do you know, is it known if there are conditions on the distribution of the unitaries, like when it will be invertible?
I think it's not.
You need like a sufficiently wide like spread, I guess.
Yeah, basically it has to be. So in the tomography world, there's a notion that we call such distribution or such measurement tomographically complete. That means there's no invisible space. Everything can be seen. It's called tomographically complete. But a full characterization of what kind of distribution is tomographically complete, what is not, there are some abstract ways to talk about them, but I don't think there's like a very efficient way to say like, oh, here's a distribution, and we immediately know if it's tomographically complete or not.
Okay, thank you.
Yeah. Okay, so after talking about this, let me jump into how to do predictions. So I'm going to erase this. Prediction is also, so far one can see like the algorithm is super simple. The prediction is also very simple. So now, instead of collect data, we wanted to predict properties. So here we're given some, let's say we pick one of the observable from that list. So we saw observable O. And now our goal is to predict the expectation value of O on this unknown state role. And the way to do that in this framework is very easy. We just say, let xt, which is a real number, to be defined by taking the trace between the observable O and this shadow that we defined, sigma hat t. So this would just be a real number. But then there's an important property we know about this xt, which is when we take the expectation value over xt, the expectation value is over what is the bit string we got and also what is the random unitary that we sampled from. By linearity of expectation, it would be transferred inside. And we know the expectation value of sigma hat t is equal to rho. So that's that identity shown there. And hence, in expectation, this real number will be equal to the kind of the ground truth that we care about, trace of O rho. But there will be statistical fluctuation, and hence there's a slight bit of complication in which we try to kind of reduce the statistical fluctuation. The naive way is just to take like the average over all of them. But here we're going to do kind of the second naive way to do it, which is we will use an estimator that's known in statistics called median of means estimation, where we just chunk up so note that there's a capital N number of them, x1 through xn, because t ranges from 1 through n. Maybe I erase that, but t ranges from 1 through n. And we just chunk it up into k chunks. So for each chunk, we're going to take the average. So x1 through x capital N over capital K. We're going to take the average. And then the same also holds for the second chunk from n over k plus 1 to 2n over k, and so on. And then so there's k chunks. Each chunk we will average over it, so there will be a real number. And then there will be k real numbers. And we just take the median and output that value. So that's known as median of means estimation. And the reason that one needs to use median of mean estimation is because sometimes there's rare events where this xt can be completely wrong. So the value might be like too large or too small, etc., or too negative. Like it can be completely wrong. And hence, by doing median of means, it allows one to truncate all that bad events and only keep like the more important part. And that allows one to converge as much faster. So now, for the remaining time, before the break, let me state two theorems about how efficient we can predict the observables. And then I'm going to pose a few questions, which all of you could think about during the break. So the first theorem considers the case when we do the example 1, so random Clifford. I'll call that Clifford. And this theorem says the following. For any observables O1 through OM, such that they're like Hilbert-Schmidt norm, or think about it as like, just like we take the metric squared and then take the trace, or also known as like Frobenius norm squared. Let's say all of them are bounded by B for all I. Then using the random Clifford measurement that we just talked about, the procedure there to collect the data, and now use this procedure to predict things, we can show that by taking n equal to order b log m over epsilon squared measurements, suffice to or maybe just that number suffice. Suffice in the sense that one can predict all of the expectation value up to epsilon error. So note that this is, especially with respect to m, there's an exponential speed up over the naive strategy where we just go through each of these observable, and for each of them we just keep measuring the state. We need to measure 1 over epsilon squared times in order to get the average to epsilon close to the true number. So the naive way would be capital M over epsilon squared, but now using this procedure, it improves to log M over epsilon squared. So that's the first theorem. And that's when we utilizes the random Clifford So the UT is a random Clifford. And next, we state the theorem for the case when it's a random Pauli measurement. That is, this UT is a tensor product of single qubit Clifford gates and measure. So now the situation is this. For any O1 through OM, such that all of them, like each of them, acts on less than or equal to k qubits, then for this situation, one can show that the number of measurements would be 4 to the k log m over epsilon squared. Suffice. So these are the two theorems that one can establish. So it essentially uses the statistical property of this median of mean estimation, which shows that how fast it will converge, like how many measurements is required to make it converge, depends on the variance of these objects, like this xi's. And now all we need to do is to analyze the variance of these objects, which, so note that previously when we were calculating this M channel, we used the 2 design property. To calculate the variance, we now need to use 3 design property. But luckily for Clifford circuits, we also know its 3 design properties. And hence, from there, one can derive these 2 theorems. So note that they're actually incomparable. So it's not true that the random Clifford is just more powerful than this randomized Pauli. It's because, for example, if some of these observables, let's say they're 4 qubit Pauli terms, Pauli operators, then it only acts on 4 qubits, and hence from here, 4 to the 4 is just a constant. But a Pauli operator, in general, or like all of these Pauli operators, when you estimate the trace OI squared, actually it becomes exponentially large. And hence, for Pauli operators, this randomized Pauli measurement is much better. But what's good about Clifford is that it works for highly non-local observables, as long as its Frobenius norm is bounded. So one of the questions that I'm going to state or write down would be kind of associated to that. Basically, when the observable O are highly non-local, act on everything, then suddenly this randomized Pauli will be very bad, because if OI acts on all n qubits, it will be 4 to the n. That's a very large number. But in that case, randomized Clifford measurement could be much more powerful. So that's the 2 theorems that one can establish about this protocol. And now, before going to, I think we're going to break soon. But before going to break, let me write down a few questions for you to think about. And it should be easy to answer based on the 2 theorems. Let me write it down here. So the first question is in regards to benchmarking. Or sometimes people call it certification. And the question is the following. So how many measurements do we need in order to check if the state that's prepared in the lab roll is close to some arbitrary target state? So there's some target state psi that we wanted to create. Maybe we have full knowledge of what psi is, like psi is in our head or it's on a computer. We wanted to prepare psi in the lab, but what we prepare is rho, and we don't really know if psi is close to rho or not, and we wanted to check that. So we wanted to check whether rho is close to psi. And the question is, how many measurements do we need in order to check that? And under the restriction that we can only apply Clifford gates. So one could first start by thinking, in general, how many measurements is required to check if rho is close to psi? So we can first ask that question and try to understand it. And then the more advanced question is, how does the situation changes when we are only restricted to performing Clifford gates on rho? So we can apply any Clifford gate we want on rho and then measure in the standard basis. How many measurements do we need in order to solve this?
So maybe this was like an open question, so this is not in the spirit of the question, but close in what sense, and what access do we have to psi?
Yeah.
Do we have all observables?
Yeah, so we assume psi is fully, let's say here, psi is fully known. Think about it as we know like the circuit for preparing psi, we know like the amplitudes for psi, everything. So psi is fully known. And yes, that's a great question. So how do we define close? Here, for simplicity, let's just say close means the fidelity is close to 1. So psi rho psi either is like maybe above 0.99 or is this like much lower? So that's so closeness under fidelity. That's the first question. And now, so one can think about that question. And here's the second one. This is a kind of a more advanced question. So for the first question, we're just trying to check if the state prepared in the lab is close to some target state. And the second question, we can think about it as, or people call it hypothesis testing. Hypothesis testing. So in hypothesis testing, in this question, it's similar. So how many measurements to find the closest hypothesis, or the closest state among psi 1 through psi capital K, or not K, maybe psi h. So there are psi 1 through psi h. We also know them perfectly, similar to like this psi. But now we have many of them. There are different hypotheses for what the state rho is. So think about it as rho is some state, and now we just wanted to figure out which among them it's closest to. And the closest, again, could be under the standard like fidelity. And the question is, how many measurements do we need in order to figure out the closest one? How does it scale with h? And how does it scale with, maybe not 0.99, but like 1 minus epsilon, say? And how does it scale with like epsilon? So that's it for now. Thank you so much.